yeah, so then if we design from scratch, then I guess that the materials, the few materials we have from Flex Motor and the part library is more than enough. So we have to create our motor catalog and then start the design through the topology. However, the topology, as I said yesterday, it needs some inputs, and general inputs: outer diameter, inner diameter, the number of slots, also the dimension of the rotor, and the number of poles to consider. Yeah, so then actually all the story and always start from the specification. The specification themselves, it can be recovered from preliminary or first system analysis, where we have a kind of raw motor parameters in order to then to fine-tune or to specify the need for this motor, because the motor is always a part of a system, and from this system we can have some, let's say, boundary condition to design the motor in terms of supply, voltage, current, and in terms of volume and weight, and of course the performances we need. Then from this specification, for sure, we have to make some first analytical computation in order to get these first parameters that we need in Flex Motor. Then when we have these first parameters, we can start with Flex Motor to study some candidates that can fit the specification. It can happen that, unfortunately, we cannot reach the performances needed with the constraints of the specification. Then here we'll have to renegotiate, if I may say that, a little bit on the specification, because physically it's not possible to put the motor and to answer the specification. Then from Flex Motor, we are not going directly to the prototyping test, because we are doing simulation in order to reduce the number of prototypes. So then we need some advanced analysis in terms of EM computation, short circuit, like as well taking into account PWM supply, and maybe for magnets, permanent magnet motor, then we need to make the demagnetization test. And if we have some advanced cooling strategy, then we need to check that as well. So this is from magnetic and thermal. We need as well to check the mechanical constraints and the NVH behavior of the motor. There are some applications that are sensitive to NVH, for instance. So this is a key point that we need. So yeah, the first analysis we are going to do in Flex Motor, they are themselves at this level already multiphysics, because we are going to study the magnetic and thermal. Thermal is always going with EM analysis. We cannot design a motor without thermal, without knowing the thermal behavior. And then, of course, the mechanical constraints need to be checked. So Flex Motor is, we can say it's a pre-designed multiphysics platform already, but we need this advanced multiphysics analysis. And of course, we can make some optimization, only magnetic optimization, or it can be multiphysics optimization. And this is the trend actually. More and more, we see this multiphysics analysis to satisfy and to optimize the motor, so it can meet the objective from magnetic, thermal, and mechanical point of view. Yeah, then we have to test again the motor in the system. And once it's okay, we have now to go to the prototyping. And the prototyping is the reference. The measurement are the reference, and then we may need to adjust some of our computation. But if we did all the multi-physics computation, normally at the end there will be a small deviation between the measurement and the simulation computation. Okay, so the specification, actually there is the specification can be different according to the application. Then we can find home appliance application, transportation application, industrial application. And then the constraints and the need is different from one application to another one. And the specification in terms of performances, thermal constraints, mechanical constraints are different as well. Yes, I have a question here. Do we receive the on-screen slides? No, the one you have, they are not grouped by slide, but you have more slides, but the same information. For me, for the presentation, it's better to group them and I will not move slide by slide. So it's the same content, but it's arranged differently from what I have and from what you have. Okay. Yeah, so then once again, the specification is something different according to the, you are welcome, Mohammed, is different according to the application we have. So what we need from the specification, actually, we need to find some geometrical constraints. So the maximum length or the maximum radius diameter that we need to satisfy the performances of the machine, like the torque, the efficiency, what is the maximum speed we need to reach. The running services, because it's different to design a motor for continuous service or for a motor that will run like 20 seconds on a high speed. There are some motors that need to run like at 50% of the performances, and then continuous running, and then we may need a higher speed, like a small time slot. Yeah, then this is something we need to know, because there is a thermal constraints which are different. Then we need to know that running services. The cooling strategy, are we going to make air cooling, or there is no cooling at all, or the motor will be on the water, or cool with a water jacket, or there will be oil cooling? So this is something we need to know. And the ambient temperature, is it 20 degrees? Is it the motor, the ambient temperature of the motor 90 degrees? Or this is something we need to know as well. And then something we need to know is the supply, the maximum voltage and the maximum current. Once again, if you have a supply that can provide 100 kilowatt, you cannot design a motor asking for 200 kilowatt actually. Yeah, so then if possible, type of the rotor, is it an internal or external rotor? If we prefer to have a permanent magnet machine or induction machine, or this is something where we need to choose actually, and usually if we need higher power density, then no doubt here is to use a permanent magnet machine. And yeah, the material preferences as well as the coil, for instance, the diameters. There are some customer or suppliers and they have some materials in their database to use, as well as for the wire diameters to use. Then we have to use them actually first. Yeah, so this is, I have here an example of a specification we may have for, this is a motor for EV application. As you can see, there are specifications on the voltage supply, the temperature range. This is the ambient temperature, of course. We have here that there is a water cooling system. The performances, we have continuous power for different speed and the peak power in motor mode and generator mode, continuous torque, peak torque, and the geometrical constraints. So with this, we have to start designing a motor. And of course, if we have already in our company some motors, for some dedicated application, we can reuse them and we can make a scale and then work on them. It's easier for us to start from an existing motor than starting from scratch. The motor we are going to have as an example tomorrow is to start from scratch from a given specification, which is more difficult actually. Yeah, so then if we start from scratch, we need, if it's like a permanent magnet motor or even synchronous reluctance machine, there are a lot of literature and we can find some equation to start with it. In what we are going to use in this in our example tomorrow is more the TRV, which is the torque ratio per volume. Then we have this feedback from previous experiences where we have a kind of motor with some TRV, and using this TRV, we can, so with few analytical computation, start to have some geometric diameters for the stator and for the rotor and the length as well, but still we need to fix as well the number of poles, the number of slots and so on. But if we have a motor in our company, in the database we have, then we can once again reuse it, so we can resize it, if necessary, rewind it. So within a given number of number of turns or number of wire in hand and so on. Then we can play and make already an optimization stuff. But if we start from a white page, this is once again more difficult because even if we have the different diameters, we can start with the TRV, but at the end of the day, we need to fix the number of poles, the number of slots, and the shape of the rotor as well. In synchronous reluctance machine, we need to fix the number of layers and the shape that we are going to consider, which is not really obvious. So there is a lot of ping pong here. We have to try test, and that's why we can have few candidates that can satisfy the specification, and then according to the maybe mechanical stress or the NVH behavior, we can choose one and not the other one. Or it can be as well the thermal constraints that can reduce the number of candidates that we can use. Yeah, once again, in the literature, there are a lot of equations to compute the different parameters of the machine. Here, in our case, within Flex Motor, we are going to use the TRB at first, and then we are going to fix some parameters like the flux density on the stator and the rotor, and the air gap, we are going to fix it as well. The flux density on the air gap, we are going to fix it as well, and the number of poles and the number of slots. But especially for the number of poles and the number of slots, there are some consideration to do and to have. The shape of the rotor as well, there are some consideration to have, and we are going to see them now. So once again, in Flex Motor, we are going to consider only inner rotor machine. So if you are going to use Flex Motor, you don't have a choice to consider only inner rotor. And honestly, we don't see a lot of outer rotor application for this kind of machine. Even if outer rotor is good for the same volume to increase the torque. But yeah, there are not a lot of discussion for us since we are going to use Flex Motor. And there are some interesting points for inner rotor. Here for the thermal and heat dissipation, it's easier to put like a housing or a water jacket surrounding the stator to help dissipating or dissipation of the heat created from Joule losses and iron losses on the stator. And yeah, the inner rotor has low inertia compared to outer rotor. So number of phases. Once again, we don't used to see a lot of like two phases or multi-phase synchronous reluctance machine. Maybe because they are we start to consider them since the permanent magnet became strategic nowadays. So maybe the synchronous reluctance machine can be a good candidate for some application instead of using permanent magnet actually, or even induction machine. So what about the number of poles? Here, especially for synchronous reluctance machine, if we put a lot of poles, for sure we will have a better torque density, but unfortunately we will increase the frequency, and we will increase the inductance then of this machine, and so we will degrade the power factor of this machine. The power factor is really I don't know how to say in English, talon d'Achille, but it's a really critical point for synchronous reluctance machines, since they have really low power factor compared to induction machine and permanent magnet machine. That's why we don't have the synchronous reluctance machine. We can see in the market there are 2 poles, 4 poles, or at least 6 poles, because more you put a pole, more you degrade the power factor of this machine actually. Yeah, so then this is about the power factor, but in other hand, if you increase the number of poles, you increase the frequency as well, and then you will increase the iron losses and the eddy current losses in AC, like AC losses on the winding or in massive part of the rotor. More you put the poles, then you can reach rapidly the switching frequency of your PWM supply. And once again, for synchronous reluctance machine, this is not an issue because we don't want to put a lot of poles because we will degrade the power factor. So we tend to limit the number of poles of this machine. Yeah, so once again, it's 2-pole, 4-pole, or 6-pole. Mainly, this is what we used to see for this kind of machine in the market. So the other consideration to do is on the number of slots, right? So high number of slots will increase the winding manufacturing cost. It's true and false in the same time because now it's a lot of machines are doing the winding. So we need to make it to choose the winding in a way to make it easier for the machine. But the winding for the for synchronous reluctance machine is always classical one, and nowadays it's not really a critical point. But larger slots, yeah. So if you have a lower number of slots, can fortunately give or degrade the dissipation between the winding and the iron of the stator. So it will increase the temperature on the wires, unless you put a lot of copper inside the slot. Higher number of slots will increase the frequency, especially. This is especially true for permanent magnet machine because the magnets will see the slotting effect, and then this frequency will be increasing due to this slotting effect, and then the eddy current will increase on the magnet. But for synchronous reluctance machine, this is not an issue because we don't have magnet, and usually we use lamination on the rotor. But there are some synchronous reluctance machine where the rotor is massive part, and here we have to pay attention on eddy current due to the slotting effect. Please note that in flux motor, you cannot do the configuration that are not physically feasible. So, for instance, if you take choose 14 poles, you cannot use 6 slots. If you choose 14 poles, you have to put the minimum of 12 slots, right? And here as well, in black, they are not feasible. So this is something helpful. If you are not, if you want to use flux motor just for studying a given existing machine, it will allow to reduce the error, human error actually, directly from the topology. Yeah, then once we fixed the number of poles and the number of slots, we have now to choose the shape on the rotor. And for synchronous reluctance machine, this is really a K point. Okay, so this is a reluctance machine, so we have to create reluctance in the rotor. So if I can make this, actually we need to have the life easier for the magnetic field going like this, and the life hard for magnetic flux line going like this. So we need to create this reluctance, and to not saturate the barriers, and we need them to be mechanically okay. A lot of things to consider. Here I put some consideration. I took mainly from these two references from Rajabi Muqaddam, RSM variable speed drive application. This is a PhD subject topic. And the other reference is Mr. Truon. It's in French. Optimisation des performances de la machine synchrone à reluctance variable. So this is an optimization of synchronous reluctance machine. So we actually, and we can see the same consideration for the synchronous rotor machine, reluctance machine, and mainly there are these parameters that make good compromise on a good torque and a good power factor. There is insulation factor, we are going to see it, the number of barriers, cutoff, saturation of the bridges, the ribs, shape of the barriers, and the location of the barriers. So let's start with insulation factor. Insulation factor is a ratio between air, actually, and iron we have on the Q direction. So as you can see here in green, we have the power factor, and in blue we have the torque. And then there is power factor. The optimal power factor is at 0.6. So here we have the torque and the power factor, and then the undulation of the torque. So we want to maximize the torque, to minimize the undulation of the torque, and to maximize the power factor. So this is where we have this good compromise. And this insulation factor is actually given directly as an output when you define the geometry of the rotor in flux motor. This is something we compute, and then we need to vary it in order to have something close to 0.6. Number of barriers. This is something we have to consider from the beginning as well. The number of barriers, as you can see here, have an impact on the average torque and the torque ripple. So here you can see the average torque value. It tends to saturate when you increase the number of barriers, and you will have as well the torque ripple theory variation according to the number of barriers. So here the most interesting one is to put most of the time 3 barriers that can satisfy in this study actually good torque and smaller torque ripple. Okay, and we can see that 4 barriers in this example lead to higher torque ripple, and we don't have a gain on the torque as much as we expect. Yeah, so then most of the time 3 barriers are okay. But yeah, it's not always true as well, because there are some configuration where we have to test actually really to test 3, 4, and 5 barriers and see which one is the best one. But most of the time you will not exceed 5 barriers actually. Something maybe to take into account is that once again the magnetic flux should move easily from one side to another. So we can naturally expect that we will have number of barriers more or less equal to the number of tooths that we want to link between one side to the other one of Q axis. Okay, so anyway, this is something we have to test, but most of the time 3 barriers are okay. And anyway, in your motor, it's not very expensive to test 3, 4, or 5 barriers. Okay, so then there is another parameter which has an influence as well on torque and the torque ripple and the power factor. So once again, here in green we have the power factor. On the top in blue we have the torque, and on the bottom we have the torque ripple. So this cutoff, this is what we call cutoff, and then the opening angle of it will have an impact actually on the performances of the machine. So this is something to test to find the right angles of this cutoff. Okay, here it seems that it is something like 0.9, for instance. Yeah, we have to make some tests including this cutoff. Yeah, then the other impacting point is the bridges and the ribs. So the bridges we have in the middle, and the ribs we have here on the circumference. Once again, we don't want to make them larger, the bridges here, because it will make the life easier for the magnetic flux in this Q axis. This is not what we want. We want really no magnetic flux going on Q axis, but only on the D axis actually. But these bridges are mandatory from mechanical point of view. And then, yeah, we have to pay attention on it in order to, because they have an impact on the power factor and the torque. And if we make them very thin, we cannot, from mechanical point of view, it's not acceptable. Then, as we can see here, the one satisfying a good torque, a good power factor, and lower on torque ripple is for the width of these bridges of 1 millimeter. We have here the ribs, right? So as well, the width of these ribs will have an impact on the ondulation, the torque ripple, and the power factor, and as well as the torque itself. Yeah, if we put them equal to 2 millimeters, we decrease the power factor. The better one is to put them as 0.2, but we increase the torque ripple. So yeah, here as well, maybe the good compromise should be 1 millimeter. Okay, so the shape of the barriers, actually, the shape of the barriers can be obtained from a full finite element computation to see how the shape of the flux lines, flux lines, how they behave if I put the rotor without barriers, actually, right? So we can see easily the shape of the barrier we want. Why? Because we need, once again, to make the life easier for these flux lines going through the d-axis, right? And then this is a good indication to start with when you design the motor. Okay, so then there is also an impact of the location of the barriers. So here I have 3 barriers, but if we put them as in equidistance, or we make a non-symmetrical one, yeah, it will have an impact, actually. So this maybe we have to test symmetrical and non-symmetrical configuration to see its impact on the torque as well as the torque ripple. So this is something we have to consider in our simulation or computation. Yeah, so to make a recap, in flux motor is easily something we can take into account is the isolation factor. So we have to be careful on it from the beginning. And the number of layers is something we can test easily as well for the same shape. We can test 3, 4, or 5 layers. Because if we have more, lot of slots, maybe 5 layers is the right one. If we have a smaller number of slots, maybe 3 barriers is the right one. So yeah, depending on the configuration we have, we may test 3, 4, or 5 barriers. Yeah, so these are the first 2 things to consider in our computation, and this is what we are going to consider in our computation as well. And yeah, the other parameters are important and interesting, but from a pre-design perspective, maybe this is something to test at the end of our design when we generated 1 or 2 candidates for our additional analysis. Okay. Then this is for the rotor, and then we have to move once again to the stator. Depending on the number of poles and the number of slots, we may have several configuration of the winding. Then what we have to pay attention is really to consider the end winding, because end winding, they are not always useful because we use a copper for nothing. They will not participate to produce the torque. But when you have longer end winding, it means that you have distributed winding. Then the distributed winding, it can be concentric or lap winding. And distributed winding is better than the tooth winding because it has a good distribution of the MMF and the winding. Then we have lower harmonic. Then we can expect lower iron losses, for instance. And the distributed winding, you will have less air or vacuum on the slots. Then the thermal conduction is better compared to the tooth winding. And then the tooth winding, it can be economical because they have smaller end winding. So we use smaller end winding. We use lower copper quantity of copper. But yeah, they do have increase the harmonics, so they will increase the losses. They will have a bad thermal conduction. So from thermal point of view, depending on the application, it can be better to use distributed winding. And yeah, for our application, synchronous reluctance machine, we don't use really to see tooth winding for this application. Most of the time, it's distributed winding actually. Okay, so this is all what I have to say for this module. I don't know if you have questions, guys. Okay. No question? If no question, we can take 10 minutes break and then come back to continue our two remaining modules. So see you at 10 minutes then. So at 4 p.m. or before 4 p.m. Okay? Thanks, guys. See you. Yep. Again, let's see if you have a question, or we can start. The second module. Merci, Guillaume. Let's start then. Okay, I am going to share my screen. And then let's talk about the electrical circuit. Yeah, let's talk about some notions of the supply. Yeah, so it's AC supply for us, for sure, for our synchronous electronic machine. Then we have to know that in flex motor it's a pure sinus supply. And then since it's a pure sinus supply, we have to talk about RMS value and the electrical pulsation. Then if we have here a voltage supply, then we have to talk about the phase angle between the current and the voltage. This phase angle is due to the impedance. So our synchronous electronics machine for sure has a lot of inductance. Then we will have this phase angle between them. The electrical pulsation omega is 2pf, and f is the frequency supply here. Then the peak value is equal to RMS root square of 2 multiplied by the RMS value of the voltage. So these are some concepts, I think you have them already. Then we have to talk about active power with what we call power factor, cos phi. So active power is multiplication of voltage by the current by the power factor. The active power or the electrical power in the machine is 3 times this one. And we have the reactive power as well. Then it's the same thing, but multiplied by sinus phi. So yeah, this cos phi, which is due to the phase angle between the current and the voltage supply. Yeah, in synchronous electronics machine, the cos phi is a little bit bad. We can talk about 0.6, 0.7, where in induction machine and permanent magnet machine, we talk about 0.8 to 0.9 or more as the cos phi. Something we need to know when we deal with the flex motor is when we talk about start connection and the delta connection. So if I go to the winding here, you will see it here. Flex motor will ask you which is the winding you want to do. So the start connection is made like this, and it's a system of 3 phase with 120 degree as a phase angle between the 3 phases, right? So this is when it's a 2-pole, the electrical distribution corresponds to the mechanical distribution. If it's a 4-pole, then we do have something else. So let me make this. So if we have a 2-pole, then we have phase A like this, A and output. Then B here and output here, and C here, and the output is here. So this is for 2-pole machine, but if we have a 4-pole machine, then you will have like this. So you have the input and the output, input and output. Okay. In case of distributed winding, so this is, and then you will see that you will have C prime, B, A prime, C to add A, and make the ROM like this. So this is when we talk about 120 degree is an electrical angle and not a mechanical angle. So this is about the star connection, and the phase-to-phase voltage is linked to the phase-to-neutral voltage by a ratio of root square of 3. Then we have this delta connection. We still have this electrical angle between the current, right? And then the voltages here we have the phase-to-phase voltage that we'll see one phase, where here the phase-to-phase voltage is seen by two phases. Then that's why we need to go back to the phase-to-neutral voltage. Okay, so here the link between the line current and the phase current is done by this same ratio or factor, root square of 3. Yeah, so for this three-phase system, as I told you, the active power is 3 times this one. Okay, so, and the same thing for the power, reactive power and apparent power. When we move to complex impedance, this is something we need mainly when we deal with induction machine. Yeah, so we have this complex. So the real part is the resistance, and the imaginary part is mainly inductance and capacitance. It can happen in your circuit. You can have this RLC component. For the motor, we used to use RL component, and most of the time, the imaginary part is due to the inductance, and the real part is due to the resistance. Yeah, so let's talk now about, once again, about electrical angle and mechanical angle. I said that electrical angle is equal to the mechanical angle if the number of poles is equal to 2, then P is equal to 1. But more than 2 poles, then the electrical angle is multiplication of the mechanical angle by P. So for 2 poles, if I can see the magnetic flux recovered by phase A. For 2 poles, if I make a round, turn the rotor from 0 to 360 degree, then I will see south and north. But in case of 4-pole machine, when I move one turn the rotor from 0 to 360, then I will see 4 times. Then I will have 2 periods actually. One mechanical period. In one mechanical period, I have 2 electrical periods. So this is really something we have to keep in mind when we deal with electrical machine. Okay, then let's talk about some terminology for the winding. You will see that we will ask you a lot on the number of turns, and this is something really a key point in the performances of the machine. The number of turns in flex motor, they are asked in the winding, and here you have the number of turns and the number of wires in hand. So the number of turns here, I have 8, and I have 14. What does it mean? If we come back here, 1 turn is like this, but I can, if I come back here, I have 14 wire in hand. So if I come to my turn, so I put 14 and I make one turn. It means if I have 8 turns, I will keep 14 in one hand, and I will make like this 8 turns. So the number of turns will play a role on production of the magnetic flux. Remember, n dphi by dt, the n is really the number of turns. And the number of wires in hand, actually we use multiple wires by turn in order to reduce the skin effect. Otherwise, if we use one big wire with a big diameter, I will use a copper for nothing because there will be a skin effect then. So yeah, using wires in hand allow us to reduce the impact of this skin effect and use a copper in efficient way. Then the bundle or a coil. This is what you are going to see in the winding. So here you have one coil or one bundle. This is a radial layout, and you have a radial view, which can be helpful as well. So if I can make one phase visible, so you can see one coil, second coil, and the third coil. Okay, then. You will see as well in flux motor that depending on the configuration, you have a number of slots and the number of poles. In some cases, you can make two layers in your winding. This is really helpful because it can help us to have more more configuration possible. So if I go to AZ, here I can put the number of layers 2, and then you will have a lot of possibilities as the coil pitch, shorter coil pitch, and more possibilities for the number of parallel paths. But if I come back to 1, I will not have a lot of configuration possibilities. Then most of the time we play on these parameters, and we look at the MMF and see always the harmonics and the fundamental of this MMF. We will see later what is MMF actually. Yeah. Then before going further, I put here a red square to check the field factor. Actually, something interesting as well in flux motor. This is it can help you to see this the view of your slot, and then maybe if you put let's say 10 wires, maybe 20, then you can see that you have this red, the winding became red, and you have this gray slot. It means that your winding is not feasible, and then you can check as well the field factor, which is not feasible and realistic. So then you have, if you need 8 slots, 8 turns, sorry. Then you have to play on the number of wires in hand really to fill the slot, because here you have a lot of area without any usage. So maybe if you need really this is what you need, maybe you have a window to reduce the size of your stator actually. And the diameter of the wires cannot be chosen as well small and small. You have to respect the current density allowed for these wires. Okay, then we have the end winding. End winding are also parameters that will increase or not the resistance. So you have to go to the end winding and choose the shape of your end winding. Then you can go to the view axial view, so you can check which one you need to use. And actually, as you can see here, is the length extension of the total extension of the end winding. So if you have, for instance, a limit on the length, so you have to really to pay attention on your end winding extension in order to fit the motor in the maximum length you have. Okay, and here you will see that the resistance of the phase, if I put this one, then you have the variation of your resistance. So the end winding has an impact actually on the resistance, then the current that needed for or asked from your machine, and then the joule losses and so on. Before going further, let me go back here because there is something I didn't indicate here. There is the insulation. So if I come back here, then you need to put maybe the insulation, the liner. Let me, if I put 0.1 like this, then you have the insulation between the coil and the stator. If you have 2 layers in your winding, so then you will have, you can see it's not visible, so I have to reduce the number of wiring hands. Then if I put the phase separator as well, you can see that it will split the slot in 2 parts. So the phase separator, if you have 2 phases in the same slot, it will allow you to avoid a short circuit between these two phases. Okay, so then let's see other terminology now. When we talk about the number of slots per pole and per phase, Z. So here, for instance, we do have 36 slots, 3 phases, and 4 poles. So if I put 36 divided by 4 divided by 3, I do have 3 slots per pole and per phase, and you can see them here. Each phase will use 3 slots. So input, output, input, output, as we said previously for a 4-pole machine. Then once we talk about the number of slots per pole and per phase, we are going to talk about the pole pitch. So the pole pitch, this is distance between the input of the coil and the output of the coil, right? So, and it's computed through the number of slots divided by the number of poles. In our case, once again, we have 36 and 4 poles. So then if I come back, 36 divided by 4, I have 9 slots. So we can compute then 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have the input and the output, right? So this is the coil pitch. And there is another terminology, short pitch or So instead of going from using the full all pitch YP, we are going to make a shorter, so the output will be shorter. This is really in order to decrease the harmonics. So this is a way to play on the winding to have more sinusoidal MMF. Yeah, so then if we talk about short coil pitch, then we are going to talk about the winding factor. And the winding factor is actually made by three factors. The first one is distribution factor, KD. And actually, if we go here on our winding, flux motor compute them automatically, right? So if I go to the winding factors, as you can see, there is distribution factor, pitch factor, and skew factor. So let's see what is all these factors. So the winding factor is multiplication between distribution, pitch, and skew factors. What is it, a distribution factor? Let's consider this example with 12 slots, 2 pole, and then we can make compute the pitch, all pitch, and then we can put inner, outer, and we can consider a phase of 5. In this example, just for this example, consider a phase of 5 turns, right? Then input, output, input, output, and so on. What we are going to do is to measure the voltage. So we are going to move the rotor at a given speed, and then recover the voltage for each coil, and recover the voltage of the full phase of all the coils in series. So one can think that the voltage, the total voltage we are going to recover is simply a multiplication of the voltage of each wire, and actually it's not the case. If we consider the voltage of the phase in blue and the voltage by multiplication by 6 of a voltage recovered by one coil, we can see clearly it's not the case. So this is really the impact of the distribution of the winding on the voltage we recover. So the voltage of this distribution factor is given by this formula for the fundamental. It's also possible to compute it for the harmonics. Anyway, the alpha here is given by number of poles multiplied by P divided by the number of slots, and Z here is the number of slots divided by the number of poles. So we can compute like this the distribution factor. Once again, in flux motor, we have it already computed, and if we go to the characteristics, winding factor, we have this, the winding factor, distribution factor. The pitch factor, there is no short pitch here, there is no skew, that's why they are equal to 1. And we have this winding factor that we will need tomorrow in our example to compute the number of turns. So flux motor give it to you, and let's talk about now the short pitch winding factor, KR. So once again, we have a pole pitch computed previously. Then we can make one slot shorter, and actually this one slot shorter allow us, as we can see here in red, to have better MMF. So it's better than this full square one, because This will allow us to reduce the harmonics. And here, if I go back to my winding, if I put the number of layers 2, then here instead of 9, I can put a shorter one. And then if I go to my winding factor, now I can see that I have this pitch factor different from 1. And actually, I come back to my characteristics in my winding. And the winding, I can see here as well the pitch factor. So then, if we have this pitch factor, it's given by this formula, where beta is the shorter factor, the shorter all factor divided by the initial all pitch actually, to have this short pitch winding factor. Of course, this is something given for fundamental. You can use as well use the same for harmonics, but in our case, we will work only and mainly on the fundamental. The other technique to reduce the harmonics is to make a skewing. So in some cases, and most of the case, it's the rotor that we skew. But it can happen that we skew the stator. And if we skew the stator, then we will see this skew factor appearing. And yeah, we use a skew technique really to reduce the harmonics, and we can mainly see it, use it to reduce the torque ripple actually. And when we use a skew technique, we are going to reduce the torque ripple. But unfortunately, we are going to reduce the torque, the mean value of the torque. Why? Because we are going to reduce the MMF created in the stator. And this skew is computed using the number of poles multiplied by P divided by the number of slots, really. So here, if I go to my stator and let me make a skew angle, maybe I will use a shift angle of 10, which is, and then if I come back to my winding and go back to my winding factor, I can see appearing this skew factor. And if I go to the characteristics, then I have the 3 winding factors, the 3 components of my winding factors in the table. And actually, the winding factor is really given by the previous different winding factor we see. So distribution factor is always here, but the pitch winding factor is not always used. So if it's not used, it will be equal to 1. The skew as well, if it's not used, it will be equal to 1. So the winding factor will be equal to the distribution factor. Okay. So let's see now the different winding technologies. We have here I am going to talk about the most known one. So here we have lap winding. If I go back to my winding layout here, right, I can see a lap winding. Or if I go back to here, I can use concentric winding. Okay. So here we have lap winding. As you can see, the lap winding is, so I go from 1 to 11, come back to 2, and then go back to 12, right? Whereas the concentric winding, I will go from 1 to 12, then I come back to 2 and come back to 11, right? So this is easy to understand. Then we can see that there is consequent pole. So the winding is distributed on the poles. So the color here in flux motor corresponds to the magnet and the pole actually. And consequent pole, so all the winding is concentrated on only one coil, one pole, sorry. Okay, here I don't have this possibility. If I go more on advanced, then I can choose per pole or consequent pole, right? Okay, same thing for concentric, and then there is a winding that we are not using in flux motor. This is a wave winding. So as you can see, it's like a wave. There is not end winding in some parts of this winding actually. This is some winding. It exists, but it's not available in the windings we offer in flux motor. Then there is another kind of winding, which is fractional winding, if I can say that. So if we make the number of slots per pole per phase and we don't find integer, so we can still use fractional winding, and this is really a headache to make it. And fortunately for us, flux motor can propose it and use it automatically. And this is, of course, if we are in this configuration where the number of slots per pole and per phase is not an integer. This is another two-thread winding. As we said previously, this is something we don't use, and we don't use to see it for synchronous reluctance machine. There is two kinds of tooth winding. The one we call simple layer and the double layer. The simple layer is not available directly from what flux motor proposes, but this is something you can do in expert mode. So you can create your own winding and create this simple layer tooth winding. Then if you have a double layer winding, this is something you have directly in flux motor, and it can propose directly. So in case you have this kind of winding, then you have to adapt your slot, right? So I go back to the slot shape, then this tooth winding is more parallel tooth, and then you can choose the adapted one here. Okay, so let's talk a little bit on the MMF, or magnetomotive force. So we use three-phase, and there is a reason why we use three-phase, and we use an angle, a phase angle of 120 between these three-phase. So what happens? First, the first phase will create what we call a pulsating MMF. So pulsating magnetomotive force, it's not moving. So if I go to my winding and go to the spatial MMF, and as you can see here, if I move, it's pulsating, it's not moving. So each phase will create this MMF. And this MMF, magnetomotive force, is computed through Ampere's law. Then make it easier on the counter when input output in this counter the sum of or the magnetic field created is equal to the current supply on this counter. This is what we have seen in our previous chapter on basic laws. So this horizontal view is something we used to see for the winding layout, right? So this is actually we cut the machine and we put it in horizontal view. So if we have like this only input output, then and we cut it so we can find input output and then again the input, right? So to make things easier, so when we move through the air gap and then we encounter one slot, if it's input, then we will move by E and we stay constant. And then we encounter the output, then it's minus E and we stay constant and then we put plus E. So then we will make the axis of this MMF in the middle, so we have minus I divided by 2 and plus I divided by 2. So this is for the simple way where we have input in one slot and output in one slot. But if the phase is distributed on 3 slots, then we are going to make the same thing. Move through the air gap, encounter the first slot, move by E, stay constant, second slot, increase by E, stay constant, and third slot increase by I, then stay constant and decrease by I, and so on and so on. And this is the MMF produced by one phase. And once again, this MMF is pulsating. It's not moving on the air gap. Okay? So then, if we consider the MMF for one phase, we have to consider its axis. So we have the phase, the axis of phase 1, axis of phase 2, and axis of phase 3. So that this each phase will create an MMF pulsating on its axis, right? And this MMF is, thanks to Ampere's law, can be easily computed from the current. Then I lost my, okay. This MMF can be computed, can be given through Ampere's law. If we know that the current on phase 1 is written by Im cos omega t, phase 2, the current on it is I2 equal to Im cos omega t minus 2p by 3. This is 120 degree. And the phase 3 is with having the same phase angle. So then the MMF is obtained through the current supply, and we will have almost the same equation with a factor of A. And then if we make a sum of these 3 MMF, we are going to create then for each time we will have a location of the resulting MMF of these 3 phases, and this resulting MMF Actually, we can see clearly it's moving and it's rotating. So thanks to these three MMF, three pulsating MMF, we can create actually a rotating MMF. So this is what we want to achieve. And in flux motor here, we can see the resulting MMF moving actually inside. And this is the first part of the rotating machine. We created a rotating MMF. Then we have to make the rotor catching this rotating MMF to move with it. Okay. And this is the end of this chapter. If you have a question, I will be happy to answer it. Otherwise, we can continue the other chapter, the last one. Okay. So let's then have a look on the Park model. Yeah, so I don't know if you remember three-phase equation or the matrix of inductances we had we have seen yesterday. If in synchronous reluctance machine we have only three phases, but you can imagine for induction wound rotor induction machine, you have three phases on the stator, three phases on the rotor. Then the matrix will be really big because have mutual inductances on the stator, mutual inductances on the rotor, and mutual inductances between the stator and the rotor. Yeah, so even if we have only three phases for synchronous reluctance machine, then we need to simplify more, and actually Park model will simplify these three phases, this matrix, only to two axes, D and Q. And actually, Park model is an artifact, a mathematical artifact to simplify that. So we can move from three phases to two axes. And you can see I0 here is a homopolar component. And since we are using a balanced three-phase system, so this homopolar component is equal to 0. And then, so remaining only this ID and IQ. It is a mathematical artifact, but in the same time, there is a physical link and a physical meaning of all these parameters. We will try to have them here. So we are going to first determine this first parameter, which is 2/3. And actually it is easily obtained from solving this equation. AI at time equal to 0 minus half of IB and minus half of IAC equal to IS. Then the Park model or the Park transformation is applied, can be applied on the current, can be applied on the voltages, and can be applied on the magnetic flux. And this is what we are going to focus, because in flux motor, if you remember, we told that we are mixing analytical computation and finite element computation in one hand, and in the other hand, we said that the voltage is equal to the resistance of the phase multiplied by the current plus dphi by dt. So if we now phi, then we can compute the voltage VA, VB, VC, and since the resistance is computed through the analytical formula as well, and then we are going to impose IA, IB, and AC and vary this current. And for each current, we can compute the voltages thanks to the magnetic flux already computed through flux 2D. Okay, I will come back to this just after. Please note that the DQ axis. So once again, if we take this synchronous reluctance machine, it's really easy to define where is the location of the axis. So it's where we have this pole, if I may say that, and the quadrature axis is here. Since we have 4-pole machine, it's not 90 degree, but it's 45 degree mechanical. But electrically, it's always 90 degree electrical. Okay? Then, if you have seen the DQ vectorial diagram of the permanent magnet machine, you will see that it's really different from that one. Because, first of all, we don't have back EMF produced by the permanent magnet, actually. But we have this kind of back EMF produced by the reluctance of the machine, mainly the inductance of the machine. So we can see clearly the voltage is equal to the current multiplied by the resistance plus dphi by dt, and here dphi by dt is produced by the variation due to the reluctance. When we talk about reluctance, is the presence of the hole inside the rotor. So this is equal to the voltage. Then our control angle, our case is C. We can see phi, the phase angle between the voltage and the current, which will give us the power factor. So if you remember, if you have seen the vectorial diagram, the control angle for the permanent magnet machine is in this quadrant. For the synchronous reluctance machine, the control angle is mainly on this quadrant. So this is really different from control strategy against synchronous machine with permanent magnet. Then we may have some magnets. Then we are going to talk about synchronous reluctance machine assisted by magnets. So we will have more or less this kind of scheme with small EMF, back EMF due to this ferrite magnet. But the control angle is always still here on this quadrant and not in this quadrant. So we have to be careful as well when there is a permanent magnet. No, synchronous reluctance machine assisted by permanent magnet. Okay, so in our case, we are talking mainly on synchronous reluctance machine without magnets. So in flax motor, we use the same strategy always, mixing finite element and analytical formula. So analytical formula is to compute the winding, the resistance, and for Park model. And finite element computation are used in magnetostatic in order to extract phi A, phi B, phi C. So then we are going to supply by IA, IB, and AC, all the three phases, vary the current, vary the position, and recover this magnetic flux on the phase A, phase B, phase C. And once you have these maps, phase E, phi A, phi B, phi C, we will apply this Park model transformation in order to have phi D, phi Q. So we are going to make the same thing for AI, AB, AC for the Park transformation, to have ID and IQ. Then we have ID, we have IQ, we have phi D, we have phi Q. we can compute torque through from these parameters. We can compute VD, VQ, then the voltage for each VD, VQ, and IDIQ. Then we have all what we need to compute the joule losses and the absorbed power, mechanical torque, and so on. Yeah, so this is the artifact arc model to make computation easier. And actually, in how things will go in Flax Motor, all the tests are available in Motor Factory, right? So once you define the design, the winding is okay, the shape of the rotor is okay, the insulation factor for your rotor, okay, the number of barriers are okay as well, and so on. Then you have to make tests. So the tests you are going to do are in Motor Factory test, and since there is no magnets on the rotor, so we are not going to talk about jogging torque, and we are not going to talk about back EMF. There is only in the test have the model in order to extract the maps, the different LD and RQ that you may need for your system analysis. And directly you have IPCN test and IO test in motor mode, and the performance mapping, right? So let's see first the working point, sine wave point. So ideally is really to make IU test. Why? Because we used to know the voltage and the current supply, and if we impose it, we are going to recover the electromagnetic performances of this working point, and then recover the control angle as well, and we can recover the ripple torque and the flux density on the air gap. Let me just say something here. If you impose, you have the initial position of the rotor, and you write your current according to IDIQ, then if you vary the control angle, you will plot this static curve, right? And this static curve will not take into account the spatial harmonics. So if you impose the current and you vary the rotor position, you will see the impact of the slotting on your torque, on this static torque. So you can see this spatial harmonic. So once again, when you use a Park model, actually these spatial harmonics are not taken into account, and we used to work on within the fundamental only. Okay, so this is the interest of IU test. Then if we can recover the C, the control angle, then we can run the IPCN test. And mainly the IPCN test, it's really interesting to have these ISO values to see if the machine is saturated. So you don't need to move to Flax 2D in order to compute the machine and then see where the machine is saturated or not. Okay. Here in IPCN test, you will see that there is a fast computation and accurate. When we see fast, it means that the computation are done through Park model. So there are some finite element computation done behind in magnetostatic application to recover some magnetic flux and then use Park model. When you see accurate, accurate is a full flux 2D transient magnetic application done behind, where actually, if I go back to sine wave test and make accurate, it allows you to compute the AC losses on the winding as well, this accurate test, and of course include the torque ripple directly with this accurate mode. But in fast mode, another thing, in accurate mode, you will have access also on the iron losses on the rotor. In fast mode, you don't have these AC losses. You don't have the iron losses on the rotor. So, but they are, as we can understand, faster than the accurate mode in terms of time computation. Okay, so as I told you, the park model, we are not including iron losses on the rotor, nor the joule losses on the rotor. So if we are going to make a power balance, it's possible through this park model, because we have the possibility to compute the absorbed power. We have the possibility to compute the current, because this is what we impose. We have the possibility to compute the torque and so on. So we have all the elements to make our computation of the joule losses on the stator winding, the iron losses, thanks to the Bertotti model and the Bertotti coefficient already computed when you defined your materials. Then we can compute the mechanical power or the shaft power if we have already indicated the mechanical power. If there is no mechanical power, so the mechanical power computed will be equal to the electromagnetic power directly. So here you can see iron losses on the rotor and eddy current on the rotor. They are only taken into account in accurate mode, not on fast mode, and not in the efficiency map test. Here, when we make the efficiency map test and the efficiency computed here, it's not taken into account the rotor iron losses, nor the rotor eddy losses as well. Okay, and this is the end of my last chapter for today. If you have questions, again, I will be happy to answer them. Otherwise, I think we are done today, and we can make tomorrow our example to design the motor from scratch. Any question, guys? All right. If you don't have question, so you are free for today, and then let's meet tomorrow and work together to design the motor from scratch. Thank you once again for attending, and see you tomorrow. Thanks, Oscar. Thank you, Slavomir. Thank you, Ramin. Thanks a lot. Thanks. See you.